I think I'm using this now. Okay. Okay, roll. Okay, Aleo Nagaris Adrian. Here. Leo Nagaris Dustin. Here. Bingy. Here. Francois. Foltz.
Here.
Himes.
Here.
Hodges.
Here.
Levitt.
Here.
Lee. Malmberg is here. Martin. Here. Medina is here. Moreno. Moreno. Here. Peruch. Salmons. Wheeler.
Here.
White. And Zaragoza.
Here.
All right. So, if I remember correctly, the last time we were here, we were discussing nomenclature. And I think the only topic left. Well, firstly, let me ask you this. Did we discuss acids and bases? No, okay, so that's pretty much the last topic in this chapter, chapter 2. All right. So let's talk about acids and bases, their properties, and then we're going to get into how we name acids and bases, right? So as you can see here on the screen, let me make this full screen. As you can see here on the screen, there's a list of properties given for acids. And the first one is that they taste sour. That does not mean you need to find that out for yourself in the lab. So I don't want anybody to be tasting acids or bases or anything for that matter in the lab, right? But there are certain substances like fruits, certain fruits that contain acids. And I'm referring to specifically citrus fruits, like lemons, oranges, and so on. And of course, we all know they have associated with them a sharp sour taste. And the reason for that is because of a particular acid known as citric acid that is present in those fruits. All right. Also vinegar, right? If you taste vinegar, you know again that it has a sharp sour taste. And that's because vinegar is about 5% acetic acid. All right. So that's another example of the sharp sour taste associated with acids. The next property listed here is that they may produce a pricking or stinging sensation on the skin. Again, please do not try that out to find that out. Find for yourself that that is true. Depending on the acid, especially when it comes to mineral acids, they will cause burns, and also depending on their concentration. For some acids, if they're dilute enough, they won't have any effect. But if you increase the concentration to a certain level, then yes, it can cause some serious damage to your skin. One property that is listed here is that acids turn blue litmus red. Now, litmus is a substance, belongs to a group of compounds known as indicators, or more specifically, acid-base indicators. And indicators are basically substances which takes on a particular color in an acidic environment, and then the color changes in a basic environment, right? So litmus basically is red in acid and blue in base, right? So if you take blue litmus, and usually it's in the form of a, well, it can be in the form of a solution, but you can also have it in the form of a paper which is soaked with that particular indicator. If you dip a blue litmus into acid and take it out, you see that the part that was submerged in the liquid will become red. So we usually use that as a test to see whether or not a solution is acidic or basic. Another property listed here is that the acids, they tend to react with many metals, and more specifically the more active metals. And I'm thinking of metals, especially in groups 1A and 2A, to a certain level, and the metals in 3A as well. In those cases, the reaction will produce a salt, which is an ionic compound, and hydrogen gas. And then another important property of acids is that they react with bases to produce a neutral product. All right, so we're going to list a list of the properties of acids, and then the next slide gives you a list of properties of bases. So again, something you should not do with that, but bases, they tend to taste bitter, and they tend to feel slippery or soapy on the skin. Again, please do not dip your fingers or pour some on your skin to find out that this is true. But the reason why this property is observed is because the base produces hydroxide ions, and the hydroxide ions will react with a group of compounds that is formed in your secretion of from your skin, oils and so on. It turns the oils into soap, believe it or not. So basically that soapy feeling that you will experience when it comes into contact with your skin is due to actual soap being formed. And bases will turn red litmus blue, right? So basically it does the opposite of what acid will do as far as litmus is concerned. And the final property here is that bases will react with acids. Again, this would be the neutralization reaction. We're going to talk about this later on, all right? But basically when bases react with acids, they tend to form products which are neither acidic or basic. Okay, so let's talk about the actual definitions of acids and bases. And there are several definitions, but the one that we'll be talking about here is the one due to this guy by the name of Arrhenius, right? And basically, Arrhenius, according to his definition, is that an acid is a substance which, when added to water, forms hydrogen ions and some other anion, all right? So that's what an Arrhenius acid is. And then according to Arrhenius, a base is a substance which, when added to water, produces hydroxide ions and cations, right? So these are the definitions that we'll be working with in this chapter. There are some other definitions which you won't get into until Chem 2, right? But for now, we'll be focusing on the definition as outlined by Arrhenius. Now, neutralization is the reaction between an acid and a base to form water and a salt, all right? And the reason why it's called neutralization is that supposedly when you have an acid react with a base, then the salt is supposed to be neutral. But what you're going to find, and again, this is something you're going to learn in Chem 2, that sometimes the salt will be acidic, sometimes the salt will be basic, and in other cases, the salt will be neutral. And it all depends on the kind of acid and base that is involved in the reaction. Okay, so the salt that is formed from the neutralization reaction is basically the result of the combination of the cation that comes from the base and the anion that comes from the acid. So therefore, the formula of the salt is based on the formula for the cation from the base and the anion from the acid. Okay, so just to give you a simple example, let's say, the acid is HCl and the base is sodium hydroxide, right? Then what will happen is that the hydrogen will combine with the OH to form water. And the sodium, which is the cation from the base, will combine with the chloride from the acid to form sodium chloride, right? So this is the acid. This is the base. This, of course, is water. And the sodium chloride is said to be the salt. The salt is formed when the cation from the base combines with the anion from the acid, right? So that's a simple example. And there are other more complex examples we're going to get into, not in this chapter, but in chapter 4, if I'm not mistaken, all right? Okay, so let me continue. So now we have this table here, which gives you a list of acids and their formulas. And what we're going to get into right now is how do we name an acid? And there are several approaches we can take, right? Let's talk about naming what we call binary acids. Now, binary acids are acids which consist of two atoms, one of which must be hydrogen, right? So, and the other atom would be a non-metallic element, like chlorine or sulfur or bromine, etc., right? So how do we name binary acids, right? Now, the binary acid is based on, name, I should say, is based on the anion from which it is formed, right? Now, if the anion always ends with IDE, such as chloride, sulfide, and so on, then basically the name of the acid will start off with hydro, then the stem of the name of the anion, and then will end with IDE, all right? So if you remember this, then you should be able to name any binary acid. Please note that there are no prefixes involved, right? So there's no di, tri, etc., all right? So here's one example, the chloride ion, right? Which is Cl minus. To convert this to the acid, we add H plus, right? So this becomes HCl, aqueous, that's important, right? So this is the chloride ion. And this is called hydrochloric acid. Now, you might be wondering, why am I emphasizing that the aqueous is here? Because there's a difference between HCl, which is a gas, and HCl aqueous, which is an acid. If you dissolve HCl gas into water, right? HCl, the name of this, as we learned earlier, is hydrogen chloride. All right. So before you add it to water, that's the name of this compound. But when you add it to water, then the resulting solution is called hydrochloric acid. All right. So that's the difference between HCl aqueous and HCl gas. All right. Another example, which is hydrosulfuric. Let me squeeze it right here. If you take the sulfide ion and add two H pluses to that, then that gives you H2S, right? And H2S is a gas, a very awful smelling gas. The smell of rotten eggs, basically. Also very toxic. And if you add this to water, right, this becomes H2S aqueous, right? So H2S gas is called hydrogen sulfide, and H2S aqueous is called hydro sulfuric acid. All right. So that's basically how you name binary acids, right? So just to recap, when it comes to binary acids, their names always start with hydro, right? Then the stem of the name of the nonmetallic element, and then ink acid, right? So hydrochloric acid, hydrosulfuric acid, hydrobromic acid, hydroselenic acid, and so on and so forth, right? That's how you name binary acids, right? Now, when it comes to oxyacids, let's see here. You know what? Let me do this. Let me add a new slide. Okay, so let's say, well, let me first define what we mean by oxyacid, right? Oxyacids, oxyacids contain oxygen, hydrogen, and another element. All right. So that's what we mean by oxyacids, right? Now, one can look at oxyacids as being derived from oxyanions. In other words, polyatomic ions which contain oxygen, right? So I'm going to show you how we go from the name of the oxyanion to the name of the corresponding oxyacid. So I'm going to use NO2 minus as an example, right? In fact, let me construct a table to make it more organized. So let me this is here. And I'm going to start off with the formula of the anion. name of an ion, and then formula of acid, and name of acid. Let me do this. Okay, so the first example I'm going to use is the nitride ion, right? NO2 minus, right? So that's the formula for the nitride ion. And remember, you will have access to the list of common ions, right? So all you have to do, if you don't know what the name is, or if you know the name but don't know what the formula is, you just consult the table, right? So if you consult the table, you'll see that the name of this anion is the nitride ion, right? Okay, now the formula of the corresponding acid is what will happen when you add an H plus ion to this, and it's going to form a compound which is HNO2, right? The name of this acid that is formed as a result of adding H plus to this is called nitrous acid, right? So please note how the name is derived, right? Basically, how we derive the name is we remove the ITE ending from the corresponding anion and end it with OUS acid. All right, that's how we derive the name of your nitrous acid from the nitride ion, right? So basically, if the name of the anion ends with ITE, then the name of the corresponding acid ends with OUS acid. All right, here's another example. The sulfide ion, SO3 2 minus, the name is sulfide. Now in this case, to form the corresponding acid, because you have two negative charges here, you have to add two hydrogen ions, and the formula becomes H2SO3, right? So therefore, because this ends with ITE, the name of the corresponding acid is sulfurous acid. All right, so again, the ITE ending is replaced by the OUS. In fact, in this case, it's replaced by UROUS, right? But basically, whatever the ending is, if it ends with ITE, in the case of the corresponding anion, then the corresponding acid will end with OUS, all right? Okay, so that's how you derive the name of acids based on the names of the anions that end with ITE. Now, let's look at another example. In this case, we're going to start off with an anion with ends, whose name ends with ATE, the nitrate ion, right? Nitrate, that's the name of this ion. So to go from this anion to the corresponding acid, we add one H plus, so therefore the formula becomes HNO3, and the name of this acid is nitric acid. So notice the difference here. In this case, the ate ending, the ATE ending of the acid will become ic acid in the name of the corresponding acid, all right? So that's basically how that is done in the case of nitric acid. So if I gave you this, SO4 2 minus, which has the name of sulfate ion, right? Then what would be the corresponding formula for the acid formed from the sulfate ion? Anybody can tell me? Yes, ma'am.
H2SO4.
H2SO4, that is indeed correct. And what do you think the name of the corresponding acid is? Sulfuric acid, very good. Sulfuric acid. So again, in this case, if the ending of the anion is ATE, then the end of the name of the corresponding acid is ic acid, all right? And that's basically how we name your oxyacids, all right? Okay, and that's basically the end. Oh, no, before, there's one more thing I need to mention. Very unique situation here. Now, there is a compound known as hydrogen cyanide, right? By the way, it's a gas, and unless you're contemplating suicide, you don't want to be breathing this gas, right? The thing about this gas is that when you add it to water, it forms an acidic solution, right? It's called hydrocyanic acid. All right? So this is HCN aqueous, right? Now, this acid is kind of unique because for one, it's not binary. As you can see, it's made up of 3 elements, right? And the other thing is it's not an oxyacid because there's no oxygen in it, right? So basically, it's kind of unique compared to the others that we've discussed. So what the powers that be decided, the IUPAC folks, they decided that, okay, in terms of naming this acid, we basically treat it as a binary acid for the purpose of naming it, right? So that's why this is called hydrogen cyanide. Right? We name it as if it's a binary compound, even though it's not, in terms of the gas itself. And then over here, in terms of the acid, this is known as hydrocyanic acid, right? Again, because even though it's not binary, but according to IUPAC, we have decided that we just treat it as a binary, complete the name on this. We treat it as a binary acid. Let me correct this. So this should be hydrocyanic acid. All right, so that's basically how we name these acids, all right? Okay, so that's basically the end of this chapter. Now, based on what we have just covered, let me just check something here in terms of the assignment for this chapter. Okay, where should I go? So we started chapter 2. Oh, did we? Did we do chapter 2 assignment?
Yeah.
No.
You
Oh,
told us to, I think, to do like the first 13.
Oh, right. Well, let me ask you this. Have you tried the first 13, as he said? See. Yeah, you should be able to do these. This one might be a bit challenging, so maybe I'll work on that one with you guys. Oh, maybe I told you the first 12, because 13 is what we just talked about, we just looked at. 13, 14. All right, so this is what I'm going to do. I'm going to. All right, I'm going to back up to number 2. In fact, we can do number 2 together, because in the case of number 2, they gave you this data right here, and they're asking for you to calculate the average atomic mass of magnesium. We did a similar example last class, if you remember. So let me hear what you have to say concerning solving this problem. What would be your approach to solving this problem? Yes, ma'am.
Multiply the mass by percent voltage.
Okay, so we multiply the mass here, which by the way, you can assume to be in AMU units, right? But what she said, we multiply the masses of each of the isotopes by their abundance. So in the case of magnesium 24, we're going to take the mass, which is 23.98504 AMU, and multiply by this. Now, this we have to express as a decimal number, so that would be 0.7870. And we work that out, and we do the same thing for magnesium 25. We take 24.98584 AMU, multiply by 0.1013. And then finally, in the case of magnesium 26, we're going to take 11.17%. I'm sorry. Not bad. Let me do the math first. We're going to take 25.98259 AMU and multiply by 0.1117. So let's see what we get in each case. So 23.98259 98,504 times 0.7870. And this you have to round out to 4 sig figs. So when I did that, I got 18.88 AMU. And then in the case of magnesium 25, it's 24.98584 times 0.1013. And we got, okay, I have to round this out for 6 figs as well. So that's going to be 2.531 AMU. And then for magnesium 26, you're going to take 25.98259 multiplied by 0.1117. And again, rounding off to 4 sig figs, I get 2.902 AMU. And then what do we do next? Add them all up, right? So let's see what it gives. 18.88 plus 2.531 plus 2.902. And in this case, I'd have to round off to 2 decimal places, right? So when I did that, I'm going to get 24.31 AMU. So that would be the weighted average atomic mass of magnesium, which is the same number as it appears in the periodic table for magnesium, right? Okay, any question about this one? Any questions? Questions? Okay, is it okay for me to clear this? All right. So that is the easier question. The harder one is this one right here. So I want you to read this question carefully, right? And let me hear your suggestions as to how you tackle this one. They gave you 2 isotopes. One of them is copper 63, the other one is copper 65, right? And they gave you that the atomic weight, now this is the average, they didn't say it explicitly, but this here is the average atomic weight of the copper, right? So basically, that's the average weight, and then they gave you the actual atomic masses of the different isotopes. So this is the mass of the copper 63 isotope, and this is the mass of the copper 65 isotope, right? So given all of these things, you know, all these different pieces of information that you're provided, how would you solve this question? And by the way, what's the question asking for? The question is asking for the percent abundance of each isotope, all right? So let me hear your suggestion. Mm-hmm. Yes, ma'am.
I just started by writing out a formula. Oh, sorry, I lost my train of thought there. I started out with how you would find, oh, geez. Thanks, just easier. Can I just show you?
All right.
Thanks, sorry. It's hard to find this.
Girl, you read that night. Very good. All right, yeah, yeah, she laid it out here. I'm just going to go through and show you.
Sorry.
Yeah, no problem, no problem. Show you how to do this. All right, so the first thing I would recognize, first thing I would state is that I would let, and tell me if this is what you did for labeling the copper 63 and 65%. I would say X represents the percentage of copper 63 and Y represents the percentage of copper 65. Is that what you did? Okay, good. All right, so we're on the same page, right? So basically, there's a relationship that we can establish between these masses here, right? And the mass here using the weighted average, the percentages of each, right? So basically 63.546 AMU would be equal to X times 63.9. I'm sorry, 62.9296 AMU plus Y times 64.9278 AMU, all right? Now, in this particular case, there are two unknowns, X and Y, which is what the question is asking for, right? Now, back in the dark ages when I was in high school, right? I remember that if you have an equation which has two unknowns, right? That means that you're gonna need two equations to relate those two unknowns, right? You cannot just relate, or you cannot figure out what X and Y would be just based on one equation alone, right? So my question to you, and don't answer that question, I want to hear what else, right? My question to you is, what would be that other equation that you're going to use in order to help you to solve for X?
Y equal 100.
Exactly. So X plus Y will be equal to 100, right? Percent, all right? X would be percentage, Y would be percentage, right? So basically we have what we call, and again, this is back in the day when I was in high school. I don't know what they call it now, but we have what we call two simultaneous equations, right? I think they call them something different nowadays, but in my day, that's what they call it, right? So now we have to solve, now we can solve for X and Y. So what we can do is, we can rearrange this equation to get an expression for Y being equal to 100% minus X, right? And then what we can do is plug in this expression into where Y is. So basically, we're gonna end up with, coming down here, we're gonna end up with 63.546 AMU is equal to X. Let me just cancel out these just to make life easier, right? So you're gonna end up with 62.9296 X plus, and then because Y is substituted with 100% minus X, we're gonna put 100% here, minus X times 64.9278 AMU, right? And then what do we do next? Well, we can, what's the word they use in math again? Distribute, thank you. Been a while. So you're gonna end up with 64.927.278. That will give you, when you multiply by 100, 62.78 minus 64.9278. Well, this is not there. All right, plus 62.9296X. All right, and that would be equal to oh, this should not be here. That would be equal to 63.546, right? So it's all a matter of solving for X. So how do we solve for X? Oh, by the way, X should be here. So how do we solve for X? Well, we try to bring like terms on both sides. So let's see, what I would do is subtract 64.649 to 0.78 from both sides. And let's see, so this will cancel with that. And the 63.546 minus 63.546 minus 6492.78. So I got minus 6429.34. And then what I would do is subtract this from this, and let's see what I get. So 62.9296 minus 64.9278. And over here, I got minus 1998. I'm sorry, 1.9982. Okay, let me erase the top part here, give some more space. Okay, so basically, this simplifies to minus 6429 point. Okay, something is wrong here.
Add.
Okay, something is off here. You know what? What I'm gonna do is, instead of using 100% here, I'm gonna use 1, which is the same thing. So let me scratch it here and put 1. That should make life a bit easier for us in terms of the math. Let me clear this here. I'm sorry about that. Let me just clear all this here. And let's see what happens. So I'm gonna end up with this being equal to 62.926x plus, now this I'll expand or distribute 64.9 278 minus 64.9278x. And then what I would do is I would subtract 64.9278 from both sides. So this would give you 0. So let's see here, 63.546 minus 64.9278. So this works out to be minus 1.3, I have to round out to 3 decimal places, so minus 1.382. And this here, which would be 62.926, and minus from that 64.9278. Okay, what did we say? 62.926 minus 64.9278. Oh, okay, I made a mistake here. This should be 92.96. Okay, so let me see here. 62.9296 minus 64.9278. Okay, so here we get minus 1.999982, right? So we can simplify an x by coming from this equation here. X, this is x here. So coming from this equation here, x would be equal to minus 1.382 divided by minus 1.9982. So let's see what that gives. And according to my calculation, this works out to be equal to 0.69 right? Which is the same thing as 69.16%. All right? And that would be for the copper 63. Right? So the percentage for the copper 65 would be for CU 65. It would be 100% minus the 69.16%. So let's see what that gives. That gives 30.83% as far as the copper 65 is concerned. So those are the answers. All right. Okay, any questions about this one? Any questions? Any questions? No questions? Okay, may I clear this? Okay, so, let me see here. Okay, that question is relatively easy. You're just asking for the element, its chemical symbol or name, and indicate the type and group to which it belongs. So just to give you an example for the first one. Potassium symbol is K, right? And the type, it would be a metal, right? And the group would be group 1A, or simply group 1, right? And that's it. And basically you do the same thing for the others, right? Okay, here it is. Scroll down. And I'm quite sure you're able to do this one, right? You're given the formulas and you're asked the empirical formula, right? So what's the empirical formula for the first one? Everybody?
3, 5, oh.
That's it. Right, and you do the same thing for the other. So whatever you got for you to do on your own. And then here you can look up the charges in the table that I provided, so not much work required for that one. Okay, so let's look at naming, right? We went through the rules for naming compounds. And or if you're given a formula, if you're given a name, how you determine the formula, right? So what do you think the name of this first compound is for number 7? A. Yes, ma'am. Now, if that were a 2-point question, you get 1.5 because you're missing one important piece of information. Can anybody tell me what that is? I'm sorry? Nope. You do not use the prefixes tri or mono or di when it comes to naming ionic compound. Yes, sir. Nope. She got it mostly right. She said chromium nitrate. But there's one piece of information needed. Yes, sir. Chromium 3 nitrate, exactly. Remember, there are certain metallic elements that can exist with different charges in their atoms, right? And chromium is one of them. Again, you can look at your table to identify those ions, right? Chromium can exist as the ion with a +3 charge or an ion with a +2 charge, right? So when you're naming these compounds, you have to indicate the charge where you have the possibilities of more than one charge existing. So in this case here, it will be chromium 3 nitrate, all right? You have to indicate the charge using Roman numerals, right? Okay, what do you think the name of the second compound is? I'm sorry, not the name. They gave you the name, what the formula is. So again, you have to consult the tables to look up the ions, and very importantly, look up the charges on the ions, because that's important when it comes to determining what the formula is. Okay, so what's the name? I keep saying name. What's the formula? AG NO3, and that's it. Right? Any questions about this one? And you'll notice in this case here, they did not indicate the charge in the name, right? Because according to IUPAC, if the ion or if the metallic element can only display one charge, right? Then according to IUPAC, you should not indicate a charge, because according to them, that's being redundant. See what I'm saying? If the ion can display more than one charge, like in the case of chromium, then you need to indicate the charge using Roman numerals in the name, right? But something like silver nitrate or something like sodium chloride, you don't indicate the charge because silver can only have one charge, sodium can only have one charge. So therefore, you don't indicate the charge in the name. Okay, what about C? What would you say is the name of this compound? They gave it a formula. What's the name? Chromium. Whoops. Chromium 3 oxide. Right? So that's basically how that is done. Let me just scroll down to see what we have below. Okay, okay, what about D? Again, you might find your tables helpful in this regard. Well, well, iron 2 nitrate, you sure about that? Nitrite. Exactly. Iron 2 nitrite. Okay, what about this one? In this case, they gave it a name. What's the formula? Lead 4 acetate. Again, you're gonna need your tables with the list of common ions to help you with this one. Yes, ma'am.
PB,
PB,
parentheses,
C2,
C2H3O2.
O2, you sure about that? Again, I'll take off half a point. Here's a hint. The lead has a 4+ charge. And the acetate has a -1 charge.
Oh, and that just before.
Exactly. So that will be the answer. Lead 4 acetate. Right? Any questions about this one? Any questions? Questions? Okay, what about F? Now, the difference between F and the others that we did before is that this is a molecular compound, a binary molecular compound, right? So in the case of binary molecular compounds, we use prefixes in most cases. Of course, there's some exceptions which we talked about, right? So, based on the name given here, what's the formula? Dinitrogen trioxide, what's the formula? N2O3. What about this one? S4N4, what's the name? That's a formula, what's the name? Tetra, no, not sulfide. Because remember, the first part, you use the full name of the element, so it's tetrasulfur. And then what? Tetra nitride. Remember, for binary ionic compounds, the second element is always ending with IDE in the name. All right? So nitrogen becomes nitride, sulfur becomes sulfide, oxygen becomes oxide, and so on. All right? Okay, any questions about any of these? Any questions? Questions? All right, let me, oops, what did I do? Let me clear this. And scroll down. Okay, last one in this question. Case yellow, what would be the name of that compound? Again, the tables would be helpful in this regard. Well, case yellow, excuse me, case yellow. What's the name? Potassium. I'm sorry, repeat that. Hypochlorite. All right, very good. Okay, let me clear this. And let me scroll down. You should be able to do number 8 because all you have to do is look up the formula for these different ions. So I'm going to leave that for you to look up. Okay. Here, the question is asking for the empirical formula for the ionic compound formed by the following. So basically, you're given the ions, which is giving you a lot because they gave you, you have these ions in the table. But anyway, what would be the formula for the result of combining the calcium with the phosphate ion in the first one? All right, so what would be the formula? Now, the key thing you need to remember is that when it comes to ionic compounds, the compound is neutral, which means that the total number of plus charges must be equal to the total number of negative charges. So as we have it right now, the charges are not equal, right? You have 2 plus charges here and 3 minus charges. So how do you get the number of plus charges being equal to the number of negative charges?
3 by 2.
Multiply 1 by 3.
The calcium.
Multiply the calcium by 3 and phosphate by 2. So when you put it together it becomes Ca3 and then open parentheses PO4 and then 2. All right. And please remember, when it comes to polyatomic ions, if you have more than one of them represented in the formula, make sure you put them in parentheses and then you put the number as a subscript immediately to the right of the second parentheses. All right. So this would be the formula for calcium phosphate. What about this one? K plus combining with NO3 minus. What would be the resulting formula? KNO3, right? What about the next one? Al parentheses OH. Exactly. What about this one? Va parentheses. I'm sorry? HCO3. And then what goes out here? 2. All right. Okay. So those are relatively easy. Go down. This is just asking for you to predict whether or not these compounds will occur. You're asking whether or not these compounds are ionic. Basically, if you have a combination of metal and non-metals, usually that's ionic. And if you have a combination of non-metals with each other, then usually that's molecular. There's one exception, and that is with the ammonium ion, right? The ammonium ion, or any compound that contains the ammonium ion. As you can see from the formula for ammonium, there are no metals present, right? But this is ionic, so when it combines with, let's say, chloride, this compound is considered to be ionic, even though there are no nonmetals, and that's because the ammonium itself is ion, all right? But apart from that, pretty much, all ionic compounds will contain a combination of metal and nonmetal, while the covalent or molecular compounds will be basically combinations of nonmetal. So in this particular case, in the case of sodium hypochlorite, this is ionic. In the case of this compound, this is covalent, and so on and so forth, right? So I'm gonna leave you to figure out the others. Let me clear this. Let's go down, see what's next. Okay, so in this exercise, you're given in the left column of this table, you're given two elements. One of them is a metal and the other one is a non-metal, right? And basically what you're gonna do is figure out what the formulas are, right? And then the name, right? Now, in order for you to figure out the formulas, again, the table that I have referred to, you're gonna find that useful for determining the formulas, right? Because what you have to do is determine the kind of ions that will be formed from these elements in the left column. So, let me help you with a couple of them, and then you can do the rest. In the case of beryllium and fluorine, when they combine, if you go to the table, you'll see that the beryllium will have a +2 charge. And the fluorine, which will become fluoride, will have a -1 charge, right? So that's what you have to work with, right? And again, if you remember what I said, the compound has to be neutral, which means that the total number of negative charges must be equal to the total number of plus charges, right? So how would we achieve that in this case? How would you achieve the number of plus charges being equal to the number of negative charges? Right, you multiply the fluoride by 2. So when you combine these together, you're going to end up with the final formula being BeF2, right? So that's how you determine the formula. Then we have to determine the name. So what would be the name of this compound?
Beryllium fluoride.
Beryllium fluoride. And that's it. Okay, any questions? Any questions about this one? Okay, so let's look at the next one. Potassium and sulfur. By the way, this is the British way of spelling sulfur. America will use F, all right? Anyway, so, potassium and sulfur, right? So, I want to hear what you have discovered about potassium and sulfur in terms of their charges. So what does your table tell you? I say potassium will have a +1 charge. And what about the sulfur, which will become sulfide? -2 or 2 minus? Okay, so how do we get the charges balanced? Multiply potassium by 2. So what's the formula for this compound? K2S, right? And what's the name? Potassium sulfide, exactly. All right, okay, so I started you off with that. You should be able to do the rest of this table. And let me just say, there's one trick question. I'm not going to tell you which one it is. I'll leave you to discover that. Let me clear this here. Let's go down. Actually, there are 2 trick questions in that one. Okay, so this is basically an exercise in naming, right? Again, I'll just do 1 or 2 of them. Let's start off with the first one, CaCl2. Again, you'll find the table is useful for this purpose. So the name of this compound would be calcium and chloride, right? You can look up these ions and you see those are their names. And let me just highlight that it would be incorrect for us to call this calcium one. Right? And the reason why is what I stated before. There are certain ions that there are certain elements that can display only one charge. Calcium is one of them. According to IUPAC, if that's the case, we do not indicate a charge, right? So the correct answer is calcium 1 chloride. Now, in the case of the next compound, things are a bit different, right? So let me hear what you have to say about the name of the next compound, number 2. Iron. What?
3.
Sure about that? Iron 2. And what's the rest? Nitride. Oops. Nitride, all right? And the reason why is because in the case of the nitride, it carries a -3 charge, and there are 2 of them, right? And let's say you don't know what the charge on the iron is, but you do know that the compound should be neutral, right? Now, in this case, there are 3 iron ions, right? So therefore, if the total charge here is -6, the total charge here will be +6, which means that each of these will carry a +2 charge. So therefore, the name of that compound is iron 2 nitride. Okay, what about number 3? Titanium 3 bromide, exactly. So again, you need to refer to the tables because the tables gives you the list of ions on your charges, right? Okay, I'm gonna leave all of that for you to do on your own. Of course, if you have any questions, what did I do wrong? If you have any questions, while you're doing it, please feel free to contact me. This is the reverse, right? I won't go through that, but basically this is the reverse of what we just did a while ago. In this case, you're given a name and you're asked to determine the formula, right? So you should be able to do those. And now we get to the acids, right? Which we just did, right? So, just to remind you quickly how we name acids. In the case of binary acids, where you have hydrogen combined with some other element, right? And the other element would have to be a nonmetal. Those acid names always start with hydro, the name of the stem of the other element, and then ic acid, right? So you have hydrobromic, hydrosulfuric, hydroiodic, and so on, right? Then we have the oxyacid. It depends on the name of the anion from which they're formed. If the anion name ends with ITE, then the name of the corresponding acid ends with OUS acid. If the name of the acid ends with ATE, then the name of the ends with ic acid, all right? So, what's the name, or I should say, what's the formula for the first acid here? What's the formula? HNO3. What about chloric acid? H what?
Yeah.
Not quite. You need something else, or you need something in addition. HCl is a different acid. Nope. The name ends with ic acid, right? So what I would do is go to the table and look up the formula for the chlorate ion. See what I'm saying? Because remember I said, if the acid name ends with, if the anion name ends with ATE, the name of the corresponding acid ends with ic acid. So what I would do is look for the formula for the chlorate ion. What's the formula for the chlorate ion? Cl. What's that? O3 minus, which means that the corresponding acid formula would be HClO3. Right? You just add an H plus to this, and you get the name of the corresponding acid. All right? Okay, what about acetic acid? What's the formula for acetic acid? What would you look for? You look for the formula for what?
Acetate.
Acetate ion, right? So you look for the formula for the acetate ion. So what's the formula for the acetate ion? Look it up, it's in the tables.
PH3,
C what?
PH3,
CH3.
CO.
Oh, okay, that's one way of expressing it. I was a bit confused. You can also express it as C2H3O2 minus, right? Okay, so if that's the acetate ion, then what's the formula for acetic acid? How will you get from the acetate ion to the acetic acid? You would add what? You add H plus, right? So the formula becomes C2H3 HC2H3O2, and that would be the formula for that. Okay. Let's look at hydrobromic acid. Right? What kind of acid is it? What kind of acids, their name starts with hydro, then you have something in the middle, then ic acid. Binary acid, right? So therefore, what's the formula for this particular acid? Nope, not H2, it's HBr, right? Now, basically, you can look at it being formed from H plus combining with Br minus. So because you have a minus charge here, you only need one H plus here. So therefore, the formula is HBr. But there's one important thing that you need to include when it comes to writing the formula for binary acids. You need to include AQ, right? When it comes to naming binary acids, you always include AQ. And the reason why that's important is because there's a difference, and I mentioned this earlier, there's a difference between HBr gas and HBr aqueous, right? HBr gas, we call that hydrogen bromide. But when you add that to water, the resulting solution is hydrobromic acid. So when it comes to naming, or I should say, when it comes to writing down the formulas of binary acids, excuse me, always include AQ. And that includes the hydrogen cyanide as well. Remember, we talked about hydrogen cyanide. If you want to talk about hydrocyanic acid, you need to include AQ. I think that's one of them, maybe down here later on, all right? Okay, any question about this? Any questions? All right? Any questions? Okay, I'm going to leave the rest for you to do in that section. You see here. Look at this. Oh, and this is the reverse. They gave you the formulas for the acids, and they're asking for you to name them. So that's the second half. Okay, and this is just basically miscellaneous nomenclature exercises. These are different types of compounds: ionic, acidic, basic, and so on. Some more here. Some more here. So by the time you're through with this, you all should be experts at naming compounds, at least at this level. Oh, hydrates. Let's talk about these briefly. Now, remember, when it comes to hydrates, remember hydrates are a special group of compounds which has an ionic part, and then you have some water molecules associated with it, right? So when you're naming these compounds, you name the ionic part just as you would do from before, right? The difference is you have to also include the number of water molecules, right? And the way you do that is that you use prefixes along with the term hydrate, right? So monohydrate, dihydrate, and so on, right? So like in the case of the first one here, where you're given this formula, the name of this compound would be calcium chloride, and then octahydrate to indicate 8 water molecules per formula unit, right? So that's how you name hydrates. So let me hear what you have to say about the next one. What do you think the name of the next one is? Iron. You're missing something.
Iron 4.
Nope. Let me write on the sulfate. So you're right about the sulfate part, right? But what's the iron 2, exactly. Iron 2 sulfate, right? And then what do you think follows the sulfate?
Hexahydrate.
Hexahydrate. All right, so that's basically how you name these compounds, all right? So if you understood those two, you should be able to do the rest. And oh, and then the second half of that problem is the opposite. They gave it a name, you have to write down the formula, right? So you should be able to do that. In fact, let me hear what you have to say about the first one here. What would be the formula for this compound? Barium phosphate dihydrate. Ba. Ba what? Ba what? Okay, so you're missing two numbers now.
3. DA3.
Ba3. Nope. What's the charge on the barium? Excuse me.
2.
Right, so you need a 2 here, right? Okay, and then what?
2H2.
Right. Oh, by the way, make sure you put a dot, right? You notice that there's a dot here, right? So make sure you put a dot here, and then, as she correctly said, 2H2O. So that will be the formula for barium phosphate dihydrate, right? Okay, so if you understand that, then you should be able to do the rest. I'll leave that for you to do. Let me scroll down. Oh, and this is just asking for the prefixes. Right, so you should know all the prefixes from 1 to 10. That's all they ask for you. And then these are some questions for you to answer. Oh, you're to fill in the spaces with these terms, right? So let's see if you can do this, right? Ionic compounds that absorb water into their solid structures are form substances called aggregate. Called what? Hydrates, okay? A compound that is completely dry or water-free is called anhydrous or anhydrate. Both mean the same thing. Anhydrous, all right? When naming an ionic substance, the name of the comes first, followed by the name of the. So what comes first? Let's look at the terms that they have up here. That's the term, those are the terms that you'll be putting in the spaces here. So what comes first in the name? Anion, exactly. And what comes next? Anion, all right? And then the prefix in the name of a hydrate indicates what? Degree of hydration. Very good. All right. So what I'm going to do is I'm going to create a drop box for this assignment right now. Here. This. Let me go to assignments. Okay, so this is assignment 2. And let me, today is the 2nd, so let me okay, I am going to set the deadline as the 4th, which would be the day after tomorrow. And let me just complete the setup here. So available from today. The 2nd until the 4th, which is Thursday. All right. So that's it. If you have any questions while doing these problems, please feel free to see me about it. All right. For discussion. Okay, I mean, yes, sir.
Is this good for the thing now?
Yeah, don't include the P, you just put mills. Mills. Mills.
Directly, right?
Yeah.
I'll scratch it out.
Yeah, the structure of the. Everything is good as far as I can see, don't see any. Skills issues. That's good.
Thank you so much.
Yeah, no problem.
See you in lab.
Mm-hmm. Okay, for those of you out there in Zoom, I'm signing off now.